expectation of a discrete random variable is just a textbook definition, and the case where it only takes positive integer values is like, you could either give this as a infinite sum, or just write it out each term explicitly, but it's gonna look a bit like this, right? So you're gonna start with n being 1, going up to infinity, probability that x equals n. Okay, we want to show that this is equivalent to this new definition involving inequalities, and this is a common trick. You can see this just by writing out the first few terms. So 1 like this, plus 2 times the probability that x equals 2, plus 3, and so on, right? But the nice way to show why this is true is we're going to rearrange what I've written just slightly. If I put all the probability 1s here, and notice I have 2 probability 2, so let's just write them as added together. And then let's say that I have 3 probability 3s. Put an x equals 3 over here. X equals 3 over here as well. And if I just kept doing that, notice that the first column, x, if I consider this first column, which will go on, I get here the probability that x is greater than or equal to 1. And here I'm getting the probability that x is greater than or equal to 2. And here, and so on, I get the probability that x is greater than or equal to 3. And this will just continue in this fashion. So I can see informally that I've argued that those statements are equivalent. You could do a more formal proof, but this is really all that's required at this stage. You'll learn more about that in your first year analysis course. So there you go. So if x is the number of boxes, then I need to open to get at least one of each kind of penguin. So notice that probability of getting a dad is p and a mom is q. So probability of at least 4. What is this? So x is the number of boxes I need to open to get at least one kind of. So if you were to open at least 4 boxes to get, at least one of each type of penguin, that's equivalent to saying when x is 3, when you've opened 3 boxes, you've got the same penguin each time. And that can either happen if you get 3 dads or 3 moms in a row. So that's where that comes from. It's pretty intuitive and obvious. And you can see that actually generalizes to the probability of x being greater than or equal to 5, for example, would be p to the 4 plus q to the 4, right? Same as getting 4 of the same one each time, and so on. So the probability of x being greater than or equal to 3, that's the same as getting the same one twice in a row. It can happen in 2 ways. What about x being greater than or equal to 2? Well, that's like either I got the dad or the mom. Or another way to think of that is this is just 1. Notice that's 1. But I'm going to write it like this, and you'll see why. That probably I need at least 1 penguin. I need to open at least 1 box to get both times the penguins. Well, that's clearly 1, right? So if I look at, why am I writing all these things down? Sorry, I should have said that, in order to find the expectation of x, we're going to use this definition, right? So I'm just going to add all those together. And this should pop out. The reason why it looks like this is probably because there's some infinite sums going on, and you can see how they would just rearrange. They're just going to be geometric series, right? So in fact, the expectation of x, I'll just write out in terms of those probabilities. So probability of x greater than or equal to 1, so that's 1. Then I have plus q plus p squared plus q squared plus p cubed plus q cubed and stuff like that, right? So actually I can nicely slot this into 2 infinite series. 1 plus p squared plus p cubed and so on. So that's the first infinite series. Then I have another infinite series, 1 plus q squared and so on. And wait, look what I did there. I added an extra 1, right? So there's only 1 in that line. Now I've added 2, so I actually need to take 1 away. You should be pretty comfortable knowing what this is. If I sum this to infinity, it's going to be 1 over 1 minus p. this guy is similarly 1 over 1 minus q. This guy is just minus 1. Notice that 1 minus p and 1 minus q, well, that's q and that's p because they sum to 1. So what's, and this would be a plus here, so 1 over q plus 1 over p, well, that's p plus q over pq. But of course, again, p plus q is 1, so I end up using that fact like, what, 3 times now? And then we just arrive at the result. And then the very last part of the question, I want to show that the expectation is greater than or equal to 3. Well, this is the same as, if this is greater than or equal to 3, I move the 1 over, it becomes a 4. And then I take this over and take the 4 down. I want to show this, yeah? So can we show that PQ is less than or equal to a quarter? That's an equivalent thing to show. Well, PQ, so I want to show that's less than or equal to a quarter. Let's write it as P times 1 minus P. Okay, so that's P minus P squared. That is, let's complete the square. So that's a quarter minus half minus P squared, I think. Yeah, hopefully we'll all agree. I want to show that that's less than or equal to a quarter. Well, yeah, it is, because canceling at the quarter, I have negative something squared is less than or equal to 0. Well, that's true. Okay, that's definitely true. So, hence the result.